这才是放在好的，这才是放好的。要不然呢？要不然呢？我给100个出来就。
啊，我跟你说了。
啊。
哦，他说他那个题目。
后边最后有反正都。三角形啊，就这样。老活了，对吧？这ChatGPT读不出图形。
王总的ChatGPT是不是应该可以？你们宿舍的俩都不来了是吧？跑完就跑。
Let's start.
So.
No. So we will continue today what we started in the previous lecture, which is the orbital magnetism of a system of free electrons. And we wrote down explicitly the Hamiltonian. We solved it, assuming that the vector potential of the magnetic field has a particular gauge, which made our life a bit easier. And we ended up with the result that the energy equal to plus mu b and n whereas the value 0, 1, 2, and so forth. And we named it the Landau levels. And for the moment, we're considering the case of 2D, which means that kz is equal 0. And I claimed at the end of the previous lecture that actually this level is degenerate. And now we would like to understand how degenerate is this level and what does its degeneracy attend. Okay, if you remember the solutions that we guessed for this system was of the structure of ikxx plus ikyy, sorry, z plus some function of x. Right, that was the solution that we started in order to get this energy. Okay, so what is the connection between the quantum numbers that we have here and the results that we got? N is connected to the x degree of freedom because that was the equation that we solved, right? For phi x. Kz we took for 2D is equal to 0. Ky doesn't influence the energy, but is still a quantum number. That's why I said that this solution is correct for any ky. Ky doesn't influence the energy as we solved it. You are actually familiar with such a situation. Could someone give an example of a situation where we had a few quantum numbers, but only one of them was relevant for the energy? Okay, that's a hydrogen atom. Remember, it had N, L, and M as quantum numbers, but the energy depended only on N. What happened with L and M? They were degenerate. Right? Any L and M that fitted with the number N gave the same energy. And you have even calculated what is the degree of the degeneracy, N squared. For the first one has no degeneracy. For the second one, where we can get different values of L and M, we have the degeneracy of 4, and so on. For 3, it was already degeneracy of 9, and so on. Okay, how can I estimate here what is the degeneracy that comes out of Ky? Okay, on face of it, if any Ky is possible, so the degeneracy is infinite. And actually it's true. For an infinite two-dimensional plane, the degeneracy would be infinite. We have infinite states for any number n. But Ky plays here a bit of a funny role. Ky does come in on one particular physical quantity. If you remember, we had x0 appeared in our equation, which was proportional to right? If to remind you the Hamiltonian, right? So what is this x0? It it is the center. What is the wave function of an harmonic oscillator? What is the main feature of the wave function of a harmonic oscillator? You remember it's some Hermite polynomial times an exponent, actually a Gaussian, which has a center at x0. So physically, ky signifies the point on the plane around which this harmonic oscillator oscillates. So if I'll go and plot the positions and so on and so forth. They actually point you on positions on the x-axis where the center of this harmonic oscillator exists. That actually makes a lot of sense. What happens to a charged particle in a magnetic field, classically? Turns around some center, right? If I'll because ky signifies a position in x.
Ky is a continuous.
Okay, now if ky is if I have an infinite system, it would be continuous. If I have a finite system, let's say I have a finite strip of width Lx, would be quantized. That's why I wrote it in this way. So for a finite strip Lx of width Lx, I have a finite number of such position as long as And this actually defines the degeneracy. If it's infinite, it doesn't matter. Ly, of course. So I'm thinking about it as a finite system with Li and Lx. Ly is defined by the usual quantization. And Lx gives me the number of position in x0 that I can be in this game. And that gives me a number where the degeneracy is given by the area times these constants according to what we got here. Now, actually, this picture helps us to understand a very important property of a two-dimensional system in a magnetic field, and that is that the current in such a two-dimensional system is quantized. And some of you have perhaps heard about the quantum Hall effect. Which experiments showing it gave 2 Nobel Prizes during the 80s. And I think just 3-4 years ago, for the theoretical explanation, was another Nobel Prize on this. And I'm not going to do the calculation, but I'll give you a flavor of understanding what happens here. Okay, if I have, let's think of it even classically, a particle in a magnetic field, what is the current that it's taking? What is the current what does flow there? Simple answer is nothing. Why? Because whatever was the initial velocity, it goes around and nothing propagates. And that is correct for all states that are in the bulk of the material. But this is a very nice observation. If I'm looking on the edge, if I have, let's say, a state here, what will happen there?
Will collide with the edge and jump along like that.
Exactly. I'll have a skipping orbit here. It will start like this, hit the boundary, and do it again, do it again, do it again. And here we have suddenly current propagating along this edge. It has a name, not surprisingly, edge currents. And if I look on the other side, if I have a edge here, basically here, take it away, okay. So I can have a state that is jumping in the opposite direction. And if I put here a potential difference, like in what I have in the Hall effect, I can populate one and not the other, and the current will correspond exactly to one propagating state. And that's the quantum Hall effect. And then the current is a current of a single electron, because it's a single state going through the system. And nowadays, the charge of a single electron is actually determined from this experiment, not Millikan's experiment, but from this experiment. And actually, this is the beginning of a whole area of research in condensed matter of topological states, because as you can see, I have here something that the bulk has no influence on it, something that happens only on the edges of the system. And why do I call it topological? Because it really doesn't matter if I have such a boundary or a boundary with a bit different shapes. The only important thing for this phenomena to occur is that I have an edge. And that's topology. Topology asks general properties of bodies without going into the details of how they are exactly constructed. And that's the same here. It doesn't matter if the strip is exactly straight. Some other situation. So I'm sure any one of you that will continue into graduate studies will run into more examples of these materials. Today it's a very hot area of research. Okay, so we understood the degeneracy. We have some hand-waving picture of the quantum Hall effect. And we started this whole game from calculating the susceptibility. Let's do it, and let's do it already for a three-dimensional system. Okay, so to remind you, what is susceptibility? We defined it as and we gave another definition which will be more convenient here to handle, which is so F is the free energy. which from thermodynamics is just up to a constant, the logarithm of z. Okay, so we know E, we have written it, well, we have already erased it. Stop. So what did I write here? I wrote down the energy, sum over all the n's, sum over all the kz's, and since for the energy doesn't depend on ky, I just multiply it by the number of states that are degenerate. Okay. So I have two summations here. Let's look into the summation on n equals 0. Okay, so basically we replace the summation with an integral. And because of the fact that we're not going over n, but n plus half, so we have a correction here. And think, how do you get this correction? Of course, you are treating half as a small perturbation over n. I can rewrite the expression that I have here. Okay. So what did I do here? I just wrote an integral, replace the summation on n plus half here by an integral on x, and wrote this term here. Okay, now a usual situation in physics, I have to decide what is important here for the quantities that I'm interested in and what is not so important. Why do we calculate the free energy? Why are we doing this calculation? We want to do a second derivative on B to get the susceptibility. So the main things that we have to worry about is getting a correct dependence on B. Let's look on the integral. We have here a dependence on B, and we have here a dependence on B. Here, do we have a dependence on B? No. So, I don't care about this term. I remain only with the integral. And what is the integral over? X, right? So if I use I can move the dependence on B out of the integral and rewrite the integral as so. Okay. How do I perform this integral? Looks a bit scary, right? Oh. Why? And what is the integral? It's only on y. Right? The rest doesn't depend on y. So this integral I can perform actually quite easily. And yet, and then I have only to sum over k, which I can exchange with integral. And I'm stuck only here with an integral, can perform the derivative on b and get and estimate this integral. And if I do it, I end up with phi equal as long as I assume that t is close to 0. Okay, so what have we learned from this whole exercise except doing some ugly integrals? Two important things. What is this part? This is a Pauli susceptibility. Which was paramagnetic. Smaller and diamagnetic in an opposite direction to the susceptibility of the spin, but still smaller, a third of that value. Why is that? First of all, why is it opposite? Because Zeeman effect basically tells you that the spin of the electron wants to arrange itself in the direction of the magnetic field. So that's paramagnetic and increases the magnetic field. What do you remember from high school if I have a time-dependent beam? What direction? And I'm pushing a field through a loop. What will be the direction of the magnetic field created by current in this loop? Diamagnetic, in the opposite direction. You can always remember that it's as if it resists increasing B and it creates a magnetic field in the opposite direction. Everything that has to do with orbital actually wants to decrease the magnetic field. Therefore, it's negative. And here in the situation where we have two opposed effects, in this case for free electrons, Pauli wins and the orbital one is swamped by the Pauli, and the susceptibility overall is 2/3 of this quantity. Okay, it seems that no one is really paying attention, and I'll stop here the course. Okay, questions? Okay, so I'll stop here. אתה יכול להפסיק את ההקלטה. וכמעט...
יעלו את זה מהגיבול. כן, את ההתלהבות של האנשים. אני נכנס רגע למזכירות. 我正在想怎么给你们讲这个特别，然后突然发现你讲